All right, let's look at some half-life problems. Radioactive isotopes decay exponentially, and the half-life is the amount of time it takes for the substance to break down, or for half the substance to break down. So I want to start with an example that's got several parts to it. Suppose you have 100 grams of a substance with a half-life of 3 days. Let's graph the amount of substance you'll have over the course of the next 2 weeks. Now, we could do this on Desmos, but I want to do this by hand. Let's see. All right, so I'm going to put the days here. Now, we're supposed to do 2 weeks. I'm actually going to go out to 16 days. Why 16? It's a power of 2. That way I can get my marks a little more evenly spaced pretty easily. Because you put 16 out there, halfway is going to be 8, halfway here is 4, halfway here is 12, then 2, 4, 6, 8, 10, 12, 14. And if I cut these in half now, I get my odd numbers. All right, so we'll do that, and then I'm going to call this 100 up here. So if we have 100 grams of the substance and it has a half-life of 3 days, at the beginning, we've got 100 grams. And then 3 days later, we're going to have half that. So if I come over here to 3 and come up to here, 3 days later, we've got half of 100 or 50. 3 more days later, we're going to go half of that and get 25. Then at 9 days, we'll have 12 and a half. At 12 days, we'll have 15. So we get these points along the curve. And if I connect those with a smooth line, a smooth curve, I guess I should call it, we get this decay. And let's see, this is 50, this is supposed to be 25, and so on. So notice, as time goes on, the amount shrinks to, well, it shrinks to 0. Now, this is a place where the model and reality are not exactly the same, because when you're talking about an isotope, eventually it's all going to go away. In theory, it would take forever for that to happen. And, you know, if you've got 100 grams of something, you know, if you've got, you know, a huge number of atoms. So eventually, if you wait long enough, all those atoms will decay, because you can't, eventually you get down to 1 atom left. You can't have half of an atom of the stuff left. So eventually it would hit 0, but our model here models it with a graph that has an asymptote. So anyway, this gives us a good picture of how it's decaying. Now, the numbers that I graphed here at the multiples of the half-life, 3, 6, 9, 12, 15, those are easy to find just by cutting the number in half. But what if you wanted to figure out how much of the substance remains after, say, 2 days? Well, we've got to find this point here on the graph. And to do that, what we need to do is figure out what this curve is. So how much of the substance will remain after 2 days? That requires us to solve the equation. So let's look at this. The half-life is 3 days. So the first thing we have to do is solve for R, because we're given all the other information. We know that we start with 100 grams. After 3 days, we've got 50 grams left. So you can take this and plug it in. You get, let's see, 50 equals 100, e to the RT, so e to the 3R. So divide that out, you get a half equals e to the 3R. So ln of a half equals 3R. So ln of 0.5 divided by 3 gives me R equals negative 0.231, and that keeps going. So that's my rate. And of course it's negative because this is a decay problem. So now that we've got that, we have to solve the equation a second time. It's saying how much will remain after 2 days. Well, let's see, A of t is going to be 100 times e to the 3, or not 3, 3 was my time, negative 0.231 t. And again, I'm leaving that 0.231 in my calculator so that I can use it with the full. I'm going to use all the decimals of precision on the calculator to calculate this. What we want to know here is A of 2. So that's going to be 100 times e to the answer times 2. See, I'm just using the answer there on my calculator to stick that number in for R. When I do that, it gives me 62.99. So 62.996. We'll round to the nearest milligram there. This many grams. All right. Now this next problem asks, how long do we have to wait for it to decay to 40 grams? Well, if we look over here, actually before we do that, let's see. What we found here is this point is 2 days, and it's 62.996. Now the other problem is asking us, how long do we have to wait for it to decay to 40 grams? So we could think of that as being, 40 is here-ish. So we're trying to find the x-coordinate or t-coordinate of this. According to my graph, it looks like it ought to be 4 point something, but that was a hand-drawn graph. It might not be that good. So let's solve the equation to get it. What we're going to do is plug into here. But let's see, we're trying to solve for t when A of t is 40. So divide both sides by 100, you get 0.4 equals e to the negative 0.231 t. Natural log both sides of this. And so you get t equals, right, natural log of 4, or 0.4, divided by, I'm just going to type this in because I've lost it on my calculator, negative 0.23104,90602. So 3.9657, blah, blah, blah. So that's how long it would take to wait to decay to 40 grams. And how's that compare up here with my drawing? Not very good. I've got it on the wrong side of 4. But that's okay. It's just a rough drawing anyway. All right. There is a formula you can get that tells you that relates the half-life to the decay rate. But I don't want to do that now because it's going to come up in this example. So suppose a substance has a daily decay rate of this. What's the half-life in days and what's the half-life in hours? Okay, so to find the half-life, what you would do, and what I was trying to say a second ago was, there is a formula you can memorize that relates these two things, but I would say don't memorize it. Because as long as you plug into our equation, you can solve these types of things. So the decay rate is negative 0.21. and it's asking what's the half-life. Well, just pick any value you want to start with. Say you start with 1 gram of the stuff, and you're asking how long does it take for it to decay to half the original amount. So I'm going to put in 1.5 there for my initial and my ending amount. You could put in 100 for A naught and 50 for A, whatever, as long as it's half that amount. So you plug this in, you get 1/2 equals 1 e to the negative 0.21t. So ln of a half is e to the minus 0.21t. Wait a second, I didn't take the natural log there. We take the natural log of the side, you get minus 0.21t. So t is ln of a half over negative 0.21. So ln of a half over negative 0.21 is negative 3.3007. Or actually, it's not negative. It's positive. So that's my half-life in days. And of course, to get the half-life in hours, you just multiply that by 24. So you get 79.216. I'm going to round that 217 hours. The thing is, since they said it had a daily decay rate, that's how we know that the original amount was, the original answer was the half-life in days. And then you just have to convert days to hours here. All right, so that's pretty much all the types of half-life problems that can be thrown at you. So I think we'll end that here. Next video, we're going to talk about exponential growth, and then we'll also talk about limited growth. So that's it for here.